Thank you, Beth, for the nice introduction, and thanks everyone for attending this talk. My goal today is just to pique your interest in the hydrology of the greater Yellowstone area and to give you an idea of what an applied mathematician does all day. So I've picked this title slide panorama painting by an artist named Henrik Iran because it really shows the diversity in the landscape we see in the Yellowstone area. And water, of course, follows the lay of the land. So this talk starts with just a brief history of how the topography ended up this way and what is the geological history behind all this. But first, to help orient yourselves, this painting is actually very accurate in terms of geography. And so you can see some of the landmarks, the Teton Range off in the distance. You can imagine you're floating above Paradise Valley, looking south here towards the big lake. And running down the center of the picture is the Yellowstone River. And behind the frame, it's going to meet up with the Madison and become the Missouri and then the Mississippi. So this is a very, very big river system that starts right here in Yellowstone, which makes it very important. It's not just the iconic park, this is also the headwaters of a very big water supply. My work, of course, is about the numbers. I'm a mathematician, so it's very much centered around this thing called the hydrograph. So I want to show you an example of a hydrograph right at the beginning here. This chart is showing us the amount of water that flows down a river on any given day. And we have field techs out getting their feet wet to collect this data. Well, what they're actually doing is calibrating an instrument that will do it automatically for us. And in the bottom photo, you see Bob, the director of YERC, the nonprofit I work for, peering at this sensor, hoping that it hasn't washed away during the flood because they're kind of expensive. But actually, Yellowstone is very well gauged. It has a lot of these instruments measuring flow along the main stem and also along the tributaries. So the example I'm showing you here actually shows two hydrographs in the same plot. One is the Gibbon River, which you'll encounter if you drive west from Gardner. And the other is at Soda Butte Creek over near Cook City. And one of my goals tonight is to try and explain this signal that you're seeing here in the hydrograph in terms of the physics and the geology and the ecology of the area. So it all starts with a history lesson. Back about 10 to 20,000 years ago, the ice ages finally ended. And before that time, this whole area was covered in ice. So this is a USGS map you're looking at that reconstructs the extent of that ice cover. And you see it goes all the way down the valley. It doesn't end until Chico, way up here. And so this is a huge mass of ice. And what this does is it carves out the landscape, carves the mountains as we know them today. And this is a very different time, not just in terms of the topography, but the ecology was very different as well. One of the things that captivated me as a biology student way back 10, 15 years ago is the Pleistocene megafauna. If you've never heard of the Pleistocene megafauna, I encourage you to go and Google this term. It's just the craziest assemblage of animals you've ever seen. You got beavers the size of small cars, and here's a bear and a grizzly and a black bear for scale comparison. And of course the woolly mammoth here. It's a very interesting time to be alive, and there are actually humans in this area towards the end of the ice ages. So we know that one of the factors in the extinction of all these gigantic animals was the arrival of human hunters. But the other component was climate change. I'm talking about the not contemporary climate change, not anthropomorphic climate change, but the end of the ice age. It was another dramatic shift in climate, and this led to extinction of these very large creatures. As the ice sheets and glaciers receded, they left behind a lot of remnants. So you can find things like these glacial erratics, giant boulders lying around where they shouldn't be. And these were deposited by glaciers, along with a whole lot of other sediment and rocky debris. And we call this glacial till. And this is just all the stuff that was scraped off of the mountains and carried down the valleys in these ancient times. Here's another example where we can see some evidence of the glaciers. If you've ever been to Chico, there's a hillside sort of on the valley side of the resort. And this is actually a moraine, which is where a glacier has bulldozed this sediment up into a big pile and formed a hill that outlines the old extent of the glacier. Today you can go horseback riding and frisbee golfing on this moraine. So next time you're out there, have a look south and just imagine the gigantic mass of ice that used to be there. Here's another example of some interesting glacial remnants. This is called an alluvial fan, and it's over in Ennis, just west of Big Sky. A creek, Cedar Creek, is carrying this glacial till downstream, and where it hits the flat part of the valley, it starts to fan out and it spreads this debris around in a very orderly fashion. And it's actually striking when you look at a topographical map. This is what we're looking at here with this diagram, USGS topo map. The contour lines are so perfectly symmetrical, it almost looks like this was man-made. But this is Mother Nature's dam. It's formed naturally, and it's continuing to form as all of this sediment gets carried down the slope. This image, by the way, is actually a textbook example. You can find it in textbooks. So Ennis is famous for that reason. Now, the reason we care about all this glacial till is that it actually stores a lot of water because it sits deep underground. Quite often it gets buried in a layer of soil, and then you have vegetation growing over top. So you can't really see a lot of this, but it's there, and it acts like a big sponge, soaking up water that's sunken down below the soil layers. And this big reservoir of water hidden underground is what we call the aquifer. And the aquifer is quite interesting in Yellowstone. It's very complicated. And it also serves a very important role. We use it, of course, for well water. It's the source of springs, but it also delivers water to creeks. And this is one reason you can get flowing water in the coldest days of winter when you might expect it to be freezing, because like the ocean, the groundwater has a very fixed temperature. It's such a massive volume. It doesn't really change temperature through the year. So it comes out as liquid water, and a lot of species are going to benefit from this. You can see some elk having a drink there at Gibbon Creek in the middle of winter. This is also helping us to explain this hydrograph a little bit better. If we go back to that hydrograph I showed of Gibbon River, you'll notice in the winter months here, October, November, December, onto March, the hydrograph is pretty flat. And so we have this steady trickle of water. There are a few spikes here and there where there's been a warm spell or maybe a bit of rainfall, but for the most part, it's this steady stream of water, which we call base flow. And this is coming from the aquifer. This is that leaky aquifer delivering water to the creeks. Now, with the arrival of spring, what happens is the snowpack up high in high alpine starts to melt. And over the course of the winter, it's been accumulating all of this water locked away as frozen ice and snow. And suddenly this water is released, and some of it goes and finds a creek right away. It runs off surface. Some of it goes into the soil and can move through the soil towards the creek. But quite a lot of it will go sink down into the aquifer. And this is how the aquifer recharges each year. So it's constantly leaking this base flow and feeding springs and wells, but it's also recharging each year with the spring pulse. And this explains the big spike you see in May, June, July, August as that glacial melt happens. And the interesting thing about this hydrograph is how different these two creeks are. Gibbon Creek is groundwater dominated, so it's mostly this base flow that you notice, and there's a smaller spike in the spring. Soda Butte Creek is located higher up where there's not so much depth in the aquifer. And so in the winter months, the flow almost drops off to nothing, and the spring pulse is much more pronounced. Water up from their roots, drawing water out of the soil that would otherwise continue on to a water course or to the aquifer. And this can be very significant. A large tree can be pulling up hundreds of gallons in a day. And in fact, in some cases, the majority of rainfall water gets returned back to the air through this process. And so city engineers actually exploit this principle, and it's become pretty common now to see people using vegetation as a means of controlling stormwater. So right next to the Bozeman Library, you've got Bogart Creek, which has been restored recently to try and regenerate some of that vegetation and help this process. And you can walk down to City Hall and check out their display about rain gardens, which do a similar thing in urban areas. Evapotranspiration is also happening in the forests, and so it helps to buffer the spring pulse a little bit and prevent big flooding events. But of course, if there's enough precipitation, everything gets overloaded and you get this giant pulse of water coming down the river system, and it's just going to go where it goes. And as we saw in June, this can mean flooding and undercutting roads and so on. So I just wanted to touch on what happened there. This has been explained as a rain on snow event. And so what that means is we had a very late spring snowfall that dumped a lot of snow up in the mountains. And then a short time later, temperatures warmed significantly and this started to melt. And then the day before the floods, we had a very intense, heavy rainfall combined with warm temperatures. This delivered a whole bunch of heat energy to the snowpack and just suddenly melted a lot of it. And this combined with the heavy precipitation led to an unprecedented amount of water coming down the river system. So you're looking at a hydrograph here of Livingston, the main stem of Yellowstone near Livingston. And it might not look all that dramatic, the peak in July or June 2022, but this is a log scale. So this peak in 2022 is actually 3 or 4 times higher than the last biggest one in the last 2 years back in 2020. So it was a significantly very unusual event that happened, of course. A lot of interesting things happen during flood events like this. We've all seen some of the destruction that can cause. There was a viral video of a helicopter flying over the North Entrance Road, and I wanted to revisit that site using Google Maps. So I've plotted where this Ranger Jake video was taken, where he's explaining the damage to this road and to other parts of the park. And what I wanted to point out here is that this is actually an example of a spot where the river has changed course. The Gardner River, in this case, it used to flow sort of to the west here. You can see the curve is sort of C-shaped in this highlighted area. And now it's inverted. It's now bending the other way. And where the river used to flow, you have all this sediment that was dumped, carried downstream. And so this is interesting because it's kind of like watching the geological processes that I started the talk with in fast motion. This is just a continuation of the same erosion process that has shaped the Yellowstone Park area. Unfortunately, in this case, it comes with a very high price tag for the parks. But we're hoping some of the work that I'm doing that we can get better at predicting when these floods are going to happen. And with that foresight, we might be able to, well, at least mitigate some of the damage. And in the future, I think we might even start using models like the ones I work on to help plan our highway building a little better and that sort of thing. However, when a flood happens, there's not a whole lot you can do. So the best thing we can do, I think, is anticipate these events so that we can plan evacuations and so on a little bit better. So how do we do this? In modeling, we always have to simplify the problem somewhat. And in this case, the way that we simplify is we imagine that all these pockets of water in the land, the wet soils, the aquifer, the creeks, and so on, we imagine they're all represented by buckets, gigantic buckets. And so you have this kind of bucket brigade where water arrives as rain and becomes runoff and then follows the next hose in the chain to say another patch of soil and then to a creek and so on. And using this model, we end up with a kind of SimCity for rivers where we can lay out the river network that we see and turn the crank and find out exactly how much water has moved into which buckets. So here's a little demo of the output of a model like this. This is at Blacktail Deer Creek, which is a neon site near Mammoth. So it's well gauged, a well studied site. And what we've done is just fed weather data from nearby weather stations into the model, into this bucket line. And then we ask how much river water is coming out of the last bucket in each day. We can go back and do retrospective studies where we look at how well the hydrograph output from this simulation matches the actual historical record. Calibrating the model is an important step here, and that means turning the taps to get the flow just right, making the buckets bigger or smaller, and so on, with the goal of basically making the output of our simulation match the record as closely as possible. Now, in reality, the area we're looking at is very, very complicated. We have a lot of buckets to worry about, and these are all interconnected. There's ways that water can loop back. There's a whole network of interconnected tributaries. Each one of these has its own little submodel, and it gets complicated very quickly. This is a map of the major watercourses and tributaries in the area that I study. You can see the park outlined in purple, and you can see there's just hundreds and hundreds of little tributaries to worry about. And this actually will strain a computer. It will slow a supercomputer down because it's so complicated. So we have to get creative to figure out how to actually run a simulation of this size. And so this is what I work on. I work on ways of using a kind of divide and conquer strategy to calibrate models of this size. And I also look at ways of incorporating variability in the weather into our simulations. Essentially what this means is we'll come up with a whole spread of weather scenarios based on the weather we've observed and feed those into the model and run the simulations and then look at the spread of outputs that we get. And so instead of just one hydrograph, we get a whole bunch of them, and we can imagine that this is kind of a distribution of possible outcomes. So we would call these predictions confidence bands. And these are very important for flood risk modeling because floods tend to be pretty unusual. This one in June was called a 500-year flood because it's supposed to happen approximately at that frequency on average. What that really means is we're looking at the long tail of this distribution, the so-called black swan events that tend to be underestimated. Our intuition tells us that they're not so common, but they're actually more common than we think. And by getting this spread of output results, we can actually put a number to how likely we think these events are going to be on any given day. And so this will help us to, for example, raise the flag when something seems to be going very wrong. But also equally important is not raising a bunch of false alarms when the model says, oh, there might be a flood. This is a big problem with disaster management. You can't just freak out every time your model says there might be a flood, because that might happen every time you run a simulation as one of the long tail possibilities. So the part of the project I'm working on right now is all about weather interpolation. So it's all about that first bucket in the line, and how do we get the information about what precipitation has fallen on any given day over such a large and remote area. And the trick we use is called spatial interpolation, and technically it's called kriging. And this is something that I've done a lot of research on. So I've written a little app to demonstrate how this works. And this is showing us the total precipitation on June 12th, the day before the flood. And so we can actually get a really good high detail level map of the whole Yellowstone area based on a small scattering of weather stations. So in this image, all of the black circles are weather stations, and you can see there's a lot of empty space between them. And so I'm working on methods for filling in that space and reconstructing this map based on only the station data. And so you can see in this example, this was a major precipitation event that hit the area on the 12th. Some places getting 6 inches in a day. This is more water than most of these places would get in the entire month. How are we doing for time? I just wanted to mention before I finish, on the mathematical side of things, the stuff I work on is not strictly about weather. It's not strictly about hydrology either. Kriging, this idea of spatial interpolation, has all kinds of applications, and they can be quite interesting. So previously I've worked on mountain pine beetle outbreak spread prediction. And it turns out we can use some of the same mathematics on that problem to create maps of where next year's infestations are likely to happen. We can also use it to take survey data on soil contamination and create a map of what we expect the levels to be at unsampled locations. So this can be very helpful for rehabilitation or for, well, any number of things. And so I just wanted to show you the kind of diversity in the applications of this mathematical technique. And kriging actually has a kind of interesting histories. So I want to finish with that. Kriging is actually very much centered around this equation here, which you can find in a paper by Albert Einstein. Now, Einstein didn't invent this. What he did was he used it to describe the motion of random motion of microscopic particles. And he used this idea to actually measure the size of the atom. But one of the things he did in this paper is he explained this phenomenon called Brownian motion, which dates back to the 19th century when the botanist Robert Brown was studying pollen, and he noticed that under a microscope, the pollen grains seemed to dance around as if they were alive, even in the still water of his microscope slide. And Einstein was able to explain this using this same mathematics, which I find quite interesting. It wasn't until a man named Daniel Krieg adapted this mathematics to work on spatial statistical prediction that it became something we would use for say weather prediction. And Krieg was interested in gold mining. He was plotting the locations of gold deposits in South Africa. So there's this very weird kind of collection of or branches of science that where very different ideas came together and converged on the same concept. And it turns out this is also useful for weather prediction and as well as mountain pine beetle and many other applications. And so I'm just going to finish with even older history. So I mentioned Brownian motion, the motion of pollen grains moving under the microscope. Well, this idea is actually even older. It predates Robert Brown by quite a long time. We can even find philosophers talking about it in ancient Roman times. So I'll just leave you with this excerpt from a poem called On the Nature of Things, where it really describes this exact same phenomenon and wonders about how it might arise, and correctly surmises that it begins with the random motion of atoms. I think this is really kind of analogous to my work. My work I view as a synthesis, bringing together many different areas of science to answer new questions. Mathematical techniques, ecological ideas, hydrology ideas, they all come together in my flood or my river flow model. And we can see how physics and botany also converge to explain something that's captivated scientists since ancient times. So I guess you could say I'm a jack of all trades and a master of none, but sometimes that's exactly what we need to answer a question like, is there going to be a flood next year? So I'd like to thank my advisory panel. At the Yellowstone Ecological Research Center, we have Bob Crabtree, Subash Lele, and Robbie Roberts, who've been a huge help in all this. And Aaron White at the Park Service and John LaFave with Montana Bureau of Mines and Geology have really helped steer this project in the right direction. So big thanks to them, and also to my tax and the University of Alberta for jointly funding this work. And thank you for listening. So please ask any questions if you want to learn more.
Thank you so much for that presentation. Does anybody have any questions? I have one. Go ahead. I was thinking about that classification of the flood as a 500-year flood, and being here in Bozeman and witnessing it, it felt more like a change in the weather caused that flood. Climate change in the weather, just like we're having a certain kind of summer that's an unusual summer. So I wonder if you have any evaluation of whether or not that was a 500-year flood.
Yeah, well, that's a really good question. So absolutely, we are in the middle of a climate change event right now, and one thing that's going to happen is, of course, average temperatures are going to rise. That's typically the number that we talk about, is the average temperature. But what's more important than that is the distribution around that number, because the summer high temperature is not going to be the average summer high temperature. It's going to be something close to that average, and a certain amount of variability around that average can be expected, and the same with precipitation. And so really what we should be concerned about is not so much the shifting average, but the shifting variability. And what we're finding is the variability will increase, and we'll see more of these extreme events in the future. So yeah, it's gloomy, but but that's the reality. And I think if there's a silver lining, we can look at the geological history and the history of life in Yellowstone, and remember that Yellowstone has been around and alive for a very long time. It will continue to be Yellowstone. It might take a different form, might have a different species distribution, and the river might change course. But well, we absolutely should be focused on that variability, because that's what leads to these extreme events, and of course that's what we're concerned about.
We've got another question. Go ahead, Sam.
There was, back on the slide with the logarithmic scale that was going up and down of like through the seasons, that
Yes.
one, it almost looks like this charge is really high, but the other factors don't look any higher. Or is that just that I'm looking at it on a small screen?
Oh yeah, sorry. I should have tidied that figure up, because it's showing, in addition to the measured discharge, it's also showing the median in orange. And I think that's probably what you were noticing. So the median, this is basically the average over about 100 years of this yearly cycle. So that will stay fixed pretty much. It will change very, very slowly, and not be affected by the kind of unusual peak that we saw. Does that answer your question? I'm looking at it now. I don't know if you can see it. Okay.
Sorry, I got confused by it. Thank you.
Oh, no problem.
And here's a question in the Q&A. Can you see that?
Oh,
and I can
looking.
read it.
Sure.
Will the peak flow of high country streams and major river stems continue to move earlier in the spring season? Have you modeled this in relation to warming of the region?
Yes, yes, to both. Very good question. That's absolutely something that's it's been observed happening this past century, and it's also something that we anticipate based on simulations. One of the cool things you can do with a model that does water cycle simulations is you don't have to feed it actual weather data. You can feed it a weather data set where you've artificially changed something. So for example, we can ask what would happen if next year it was 2 Fahrenheit higher average, and then see the result. And as you said, it will result in earlier spring peaks, and it will result in more pronounced peaks. And then the result of that, of course, is that this sort of recession period towards the end of summer will also be shortened and will be advanced to earlier in the year. So this has big effects. Actually, there's a very good climate change report on the Yellowstone area that I can link you if you want to read more about it.
Yes, thank you. If you drop that in the Q&A, that would be great.
Sure, yeah.
And we have another question.
You showed on the hydrograph for the Yellowstone River during the peak of the flood at Livingston, around 60,000 CFS. Is that close to what that graph showed?
Yeah, that's correct.
And then I've looked at USGS at Corwin Springs upstream quite a ways. And as I recall, it approached closer to 80,000 CFS. So I was curious if that's accurate. I was curious why the gauge down by Livingston, which should receive more flow from other tributaries in the gap there between the two, why that flow, the peak flow was 20,000 CFS less, unless I remember incorrectly.
I haven't looked at that hydrograph, so I can't tell you if that's accurate. But I would guess that if it is accurate, and we're seeing higher flow upstream, then what's happened is there's been some leakage into the aquifer. So I mentioned that the aquifer can receive water, or sorry, the aquifer can leak water into a creek, but it can also do the opposite. When the water table gets low, you can have water leaving a riverbed or a creek bed and entering the aquifer. That's quite a big difference, though, that you mentioned. So I'd have to look at that.
If you get a chance, take a look. Maybe the memories are on. But the other thing I wondered is downstream at Livingston, if the water was able to get around the hydrograph or the morphology of the stream, and so I wasn't accurately measuring all the water that was passing.
Yes. Okay. And that's another great point. Is these hydrographs, the instrument that measures them is actually looking at the water pressure and the kind of difference between that and the air temperature, or sorry, air pressure, which tells you basically the weight of water that's moving, and then you multiply that by a number that accounts for the fact that you have a cross section of the stream that's kind of this half moon shape, and it'll be a slightly different shape on different streams. So there's a whole process to calibrate that measurement and do the correct scaling. And my guess is that at the peak of the flood, you had riverbanks eroding and changing shape, and this would have kind of messed up the calibration of that instrument for that particular moment in time. So certainly I would take the instrument measurements from this period with a grain of salt for that reason. You'll notice on this USGS plot, there's a pink line here for the past few months, period of provisional data. Before that, period of approved data. So a USGS is going to go and do quality control and look at things like that, I believe. It could well be that we never get a very good estimate of what the actual discharge was, simply because it was so chaotic and the riverbank was being eroded so quickly.
Yeah, well, thank you.
Good question.
Hey, Billings has a question. Is it okay?
Oh,
Go ahead. All you.
I tracked a flow in the river here in Billings, and it's quite a bit higher this year. It's been high all summer long than last year. Is that entirely a reflection of how hot and dry it was last summer? And how comparatively wet it's been this year, or is there something going on with the aquifer as well?
Oh, that's a good question. I imagine your first guess is probably correct, but to be honest, I haven't looked very carefully at the last 2 years of data yet in my simulations. I've actually been mostly focused on historical periods where we had really good weather data for various reasons. The process that I'm working through right now is calibration, and so we look at historical periods to do that. But when we finally get to that point where we're running simulations up to present day, those will definitely include the last 2 years, and they will give us an opportunity to do kind of a postmortem and look at different sub watersheds in the Yellowstone area and find out what's happening in each of those individually. So we could answer that question with some more certainty later. But
Okay.
Yeah.
Thank you.
Thank you.
Dean, you mentioned that you don't want to be too quick with your modeling to say that a flood is imminent. You want to be careful about releasing that data, because obviously the scare involved in it. But I'm just wondering if you could speak a little bit about the signifiers that do make you say that it is imminent. How do you guys manage that kind of dance of when to release and when not to?
Yeah, that's a really good question, and that almost gets into I guess HR stuff that I'm really not an expert in. What I think we're going to do, I'll explain the process that I'm imagining. We'll run our simulations. We'll run a whole spread of weather data, and hopefully get a spread of outputs that is statistically principled, meaning we're going to attach to each one of those simulation outputs we'll have a probability, and we'll say, this is the most likely one, so that's our prediction. But then we'll have other ones that are, slightly less likely, and so on. And once we have that, we can start to ask questions like, what is the maximum flow rate that we can expect 95% of the time, given these particular conditions we're experiencing now? And so that'll give us, what we call a 95% confidence interval for the flow. But the point of this is that we can set that confidence level to whatever value we want. So we can work backwards, and we can say, well, how often is it reasonable to alert the public to a flood risk, given the resources we have, and so on. And then we'd pick that number. It might not be 95%, but it would be, some number, some probability. And we'd say whenever we see a massive flood event falling within this confidence window, then we sound the alarm. So that would be the process. It would be based in statistics, which would allows us to control the false positive rate. And that's really the goal of this work I'm doing on the weather stuff.
Thank you.
Yep, you're welcome.
Well, we'd love to have your team back and get a presentation on that data when that's available.
Oh, yeah.
Okay. If there aren't any other questions, and I'll just wait a few seconds, see if there are. Thank you so much, Dr. Cook. That was very interesting. It's just very worthwhile to understand what's happening to nature around, and you really did explain it well.
Oh, you're welcome. And just before I forget, that climate change report I mentioned, you can find at gyclimate.org. It was released last year. It has some very good science in there. Steve Hostetler, Kathy Whitlock, Brian Schumann. So check it out if you're interested in the science of climate change. Very good read.
Okay. And thank you, all 25 people who attended tonight, taking time to attend. That is quite an accomplishment on such a beautiful evening.
Yeah.
As I said, we're going to put this, we've recorded and we'll have this available on the Bozeman Public Library YouTube page. And I'll be in touch with Billings and see what they want to do. Thank you, Billings Public Library, for supporting our program tonight.
Thank you, Bozeman, for inviting us, and thank you, Dr. Koch. We appreciate it.
You're very welcome.
And with that, we will say good night.
Good night.
Good night.